Hi S4, it's Mr. Bull here. It's a beautiful day outside, hence the strong sunlight and the shadows. But we're moving on to the next installment of our National 5 Physics, and that is the conservation of energy. Now we've been looking at three different energy equations over the last couple of weeks: kinetic energy, work done, and potential energy. How does that all come together? Well, it comes together with the law of conservation of energy. So the definition says, the law of conservation of energy states that energy cannot be created or destroyed. And if you hear anything in the background, it's just Nova doing her thing. So, energy cannot be created or destroyed. It can only be transferred. Right, what does all that mean? Well, let's read it again. The law of conservation of energy states that the energy cannot be created or destroyed. It can only be transferred. Okay? So that means that there's all this energy that exists out there that just moves from one form to another. It's not created and it's not destroyed. So, if we were to take a mountain or a hill analogy, and I hope we're all looking forward to getting back out in the hills and doing some walking, but if we were to look at this and we have someone at the start of the hill. Now that person at the start of the hill, and you could see even that they've had chemical energy by the amount of food that they've eaten, and that energy is now within them, they're going to have to do work or work done to move themselves from this position to the top of the hill. So they're going to be going in this direction, and they're going to need EW equals FD, some sort of force they put in over a distance. Okay? So they're putting in the work. Now that work can be tiring, it can be exhausting, and if you've ever been up a hill, you'll know that that's what it feels like. It feels exhausting and tiring and sweaty to get up to the top. But when you're at the top, what do you have? You have some sort of height, don't you? So that height comes in the form of potential energy, because EP equals mgh. So you now have this potential energy at the top because you've gained some sort of height. Okay? Now, when you're at the top of the hill, there's a number of ways you can get down. Most of us would probably walk, some of us might run, and if you were really adventurous, you could maybe paraglide or do something like parachute. But let's take the analogy that if the mountain or hill just disappeared, what would happen to us at the top of the hill? Well, it would just transfer into some sort of movement energy or kinetic energy. So to get to the bottom of the hill, we would need to have had some sort of kinetic energy. So that potential energy at the top has now transferred to kinetic energy as we then go down the mountain. So, say chemical energy in the form of food allows us then to do work to get to the top of the mountain. All that energy is now transferred into potential energy. It's not been created or destroyed, it's just been transferred. And that potential energy is then transferred straight to kinetic energy as we then travel down the mountain. So what we can say is that EW equals EP equals EK. In other words, work done equals potential energy equals kinetic energy. And that is going to help us when it comes to examples where we need to work out potential energy when we only get given the values for, say, work done. I'm going to explain those examples after this wee clip of me in the hills showing you what this looks like. Hi S4, Mr. Bull here again. Right, I'm going to be climbing up this hill to show conservation of energy. I've had my breakfast, I've had chemical energy, and I'm going to be doing work done, remember, force times distance, and I'm going to be exhibiting that going up the hill using doing work. Alright, so here we go. There we go. And now, after that work done, it's transferred to potential energy because I've gained some sort of height. Remember, EP, potential energy, equals mass times gravity times height. And I'm at my highest height now, and that is me got potential energy. So what I'm now going to look at is kinetic energy. Right, kinetic energy. Potential energy at the top, and that made way for kinetic energy really fast coming down the hill. So we went from work done to potential and then back to kinetic energy. That is conservation of energy, and I hope it makes sense in terms of that hill there. Right, S4, let's do some examples. Hi S4, hope you enjoyed that little clip. Let's now talk about examples regarding conservation of energy. So the first question says, a 40 kilogram box is dropped from a height of 20 meters. What was the box's potential energy before the drop? Right, so this should be a fairly straightforward equation. EP equals mgh. We know that from the last couple of weeks. Mass is 40 kilograms. Gravity on Earth is 9.8. And height is 20. So that actually gives us a potential energy of 7,840 joules. Now, that's very straightforward. It's number 2 that is a sneaky bit that we need to learn this week. And it says, what kinetic energy does it have when it strikes the ground? Now, looking at the information we've received, we don't have any velocity, so we can't actually figure out EK equals a half mv squared. What we need to say is this: by conservation of energy, the potential energy transfers to kinetic energy. Now, that means that EK, or EP, we can say this, EP equals EK, just like we had in the beginning of the video, which therefore means that that is equal to 7,840. So the kinetic energy at the bottom, when it strikes the ground, is just the same as the potential energy, because it transfers, it's not created or destroyed. Exactly what the law of conservation of energy says. So now that we have the kinetic energy, which is 7,840 joules, the same as before, it's now the third question saying, what is the speed of the box when it strikes the ground? So we're going to have to use maybe our little triangle to help us here. EK, and we've kind of got a half here, mv squared. We want to find the v, and this is when it gets a little bit tricky. We need to do some algebra. But once you do that, and I'm going to let you do that yourself, you get 2ek divided by m. Alright? Now we have everything we need. We've got 2 times 7,840 divided by the mass, which we already know is 40. I'm going to do that in the calculator. I get 19.8 meters per second, which is reasonable. That sounds like a good answer to me. So, hopefully that all makes sense, and that's the first example. Okay, that's us looked at example 1. Now let's look at example 2. So example 2 says this: a 1,000 kilogram car is at the top of a 50 meter high slope when the handbrake fails. Assuming no friction, A, calculate the potential energy at the top of the hill. So the potential energy, we've seen this before, we've done it before. EP equals mgh. Now the mass in this one is 1,000. We know that gravity is 9.8 on Earth, and we know that the height in this case is 50 meters. So we put that in our calculator, we get an answer of 490,000 joules. Okay, 490,000 joules. Now, B says, what is the kinetic energy of the car at the bottom of the hill? Well, it's exactly the same kind of question we looked at last time in the first example. And we just say, by conservation of energy, the potential energy transfers to kinetic energy. So EP equals EK equals 490,000 joules, because it's the same, it transfers. Okay? Right, that's B. Alright, so we know that the kinetic energy is now the same as the potential energy, so we're going to use that for question C, which is calculate the speed of the car at the bottom of the hill. So we know just from last time, I'm just going to do this equation straight up, and it's 2EK divided by M. So we now know that it's 2 times 490,000 divided by the mass, which was 1,000. So when we do that, we get a speed of 31.3 meters per second, which is our speed. Okay, so hopefully that makes a little bit of sense at the moment. Now, the last question, this one, a wee addition compared to last time. It says, why would the answers to B and C be different in real life? Well, think about it. Not all of the energy is going to go into the moving of the car. There might be some heat energy with the tires and the road. There might be some sound energy coming from maybe the tires on the road, or coming from, I don't know, the wind, or maybe the fact that there's actual in real life, there will be friction and there will be lots of other forces acting. It's not going to be the same as what we calculated out in part A for the potential energy. Hi S4, hope you enjoyed the video. Just had to cut it a little bit short there just because of the upload to YouTube, but hope you have a great week, get the questions done, and enjoy the weather while it lasts.